Good. And we are working on the free response number 2 from the progress checks for mechanics that were provided to us by AP on AP Classroom. They're also open over there. And we'll work our ways through 2 right now, then comes 3, whoopsie, and then comes 4. Whoop, I did the American 3 and the German 4, is that funny? Okay, good. So let's see what we got. So first problem, we've got a block on an incline like that, and we have an angle down here, okay? And we're not changing the angle, we're just letting this thing slide on here. There's the mass M, and let's talk about it. We've talked about this so much that we should be pretty much excited when we see this kind of problem if they gave this to us. What are the forces acting on this object initially, assuming it's not moving? Just shout it out.
Gravity.
Gravity straight down, mg, fg, and I like abbreviating it fg like this. One right next to it, mg, that's classy, but you don't have to. Fg is sufficient. What other forces?
The normal force.
Normal force, nice. There you go, normal force. And of course, the normal force is also equal to mg, right?
Depends.
No, it's not. Okay, it's not important. It's not equal to mg in this case. It's really kind of important to remember that there's no equation for normal force. In order to find the normal force, we'll have to use Newton's laws. And then, of course, there's one more force. What's that?
The force of static friction.
Friction, exactly. Friction is going to be upslope. There we go. F, there you go. And I'll leave the subscript, you're right, initially it's static. We're going to make it move, though, in a second. So I will not label it because it'll be either way upslope.
Wouldn't normal force be cosine mg?
Yeah, we're going to get to that. That's right.
Okay.
So in this diagram, that angle is the same as this angle because they're vertical opposite adjacent angles or some stupid thing, complementary, who cares? It's the same angle anyway. I'm kidding. Math's awesome. So theta's there, okay? And then we can need to split up into the coordinate system like that, x and y, to make it easy to work with. And then we have down here f, g, x, and up here we have f, g, y. And I think that's a beautiful free body diagram, but the AP is kind of ambivalent about this. They don't like this because they say, well, it looks to me like you're drawing 3 different forces down here. I'm like, you're stupid. No, this is the force, and this is breaking up into components. I don't think that's going to be an issue tonight, but just to keep that in mind if you have a crazy physics professor later on. Okay, so we've got that all lined up. Then we have our x direction, following our monkey recipe. What force is acting down slope?
Fg sine theta.
Okay, let's just write it down as FGX for now. Is that cool?
Okay.
And then upslope is?
Friction.
Friction force. And we're not going to subscript that because we're going to have the same equation for static and kinetic. And if we take in the possibility that the situation is static or kinetic, what should we write on the right side?
0.
Yine, that would be if it's static. If it's not static, it would be.
Oh, sorry.
It's okay.
MA.
MA, okay, good. And then of course, technically a 0 acceleration is not excluded, right? So Newton's first law is a special case of Newton's second law, right? Because it's a special case for 0 acceleration. Okay, so this is the fine representation. If you put the S here, this would become 0. If you put the K here, in that case, it would not be 0, okay? And then of course in the Y direction, what's the upward Y force?
Fn.
Normal force.
And there we go. And what's the downward force?
Fgy.
FGY, and that whole thing is of course equal to
0.
0. There you go. It is equal to 0. Okay, good. So we've got that nicely lined up here. Good. That looks nice. I like it. And we can now go and take those 2 equations whoop, and scroll down and put in the stuff. So this would be mg would be fg, and then x will be sine theta. These Schneider pens are awesome, by the way. Don't you like them? I think they're really good. I'm surprised I didn't know about these. They're really, really good. So now we have force of friction, okay? And we'll leave it in there because we're not sure what to do with that. And initially in the problem, they're asking for 0 when it's not moving, eh? Is that true? Good. There you go. Not moving. And then if it's not moving, this would be S. Agreed? Okay.
Mhm.
And then here Fn is, of course, Fn. And then we have minus mg cosine theta equals 0. All good? Is this too easy? Are we okay? Good review?
Good
Or
review.
good review? Okay, good. Now they said, what's the maximum angle where it can be lifted to for it not to slide? Anytime you see in a problem like this a extremum, like maximum angle, minimum speed, maximum speed, those kind of things, right? Then you know that you can do what?
Set FFS equal to mu S Fn.
Good. Super. So in general, it's true that FFS is smaller or equal to mu S Fn, which means, of course, that there's a maximum value for the friction force. Whoa, that's not on the screen. There we go. There is a maximum value. And then you got to kind of look for what's the steepest angle, what's the minimum coefficient of friction. You get the idea, right? So any of those really, you can say, okay, well, in this case, because the problem tells us what's the maximum angle, at theta max, right, it is true at theta max FFS is equal to, oh, I'm actually really glad we're having this conversation because on the exam, right, they might ask you to word that, right? Right? So,
Mhm.
you know, how would you find the static friction force, right? And you could say, because we know this is at the maximum angle, we've reached the maximum friction force, therefore friction force is equal to the coefficient of friction times the normal force. And then, you know, something like that. You know what I mean? Just putting it in words. So it's actually what we're doing, talking about is actually helpful. So we've got that. We can plug that in there. Okay. And we can also kind of smush it a little bit. I'm going to smush it a little bit like this. We're going to take this equation here. I'm going to say, okay, this is Fn equals mg cosine theta. Okay. And then we're going to take the top equation where we have mg sine theta minus FFS. Minus FFS is, of course, mu s Fn. And first, we're going to move that to the right. And we're going to plug in mu s times Fn for the friction force. And Fn, of course, we just found that to be mg cosine theta. We put that in. Mg cosine theta. There we go. There's our relationship. And we can now look at it and say, oh, cool. We can cancel out the mass as long as the mass is not 0, not allowed to divide by 0. And you can divide by g, and as long as g is not 0. This problem will not work if you try it in 0 gravity. That makes sense. You won't have blocks sliding down inclines in that situation. Okay, so here we go. Sine theta equals mu s cosine theta. Slipping a little bit into my southern accent. Hope you're not bothered by that. Okay, and then, of course, mu s is equal to tan theta, and it will be mu s min, and that's not what we're supposed to solve for, right? We're supposed to solve for the minimum angle, okay? So we kind of got to rearrange that. So this is mu s min to make it hold at a certain angle, or we can look at this in terms of solving for theta. Let's do that over here in blue, black. So that would be theta max would be equal to, you guys like writing this like this. So we'll do that. Tan minus 1 of mu s. There we go. And if you're hyper nerdy, you'll be like, that's 1 divided by tan. So this is really the arctan. Okay, so it depends on how nerdy you are, whether you're okay with the tan minus 1. That's what your calculator says. But of course, that really means 1 divided by tan. And this is actually the inverse tangent function, also known as arctan or atan. Okay, you guys chill? So chill you fell asleep? Well, look at all these people who showed up. That's so cool. Okay, no feedback now. The group is too large for feedback. Okay, I'm going to take a picture of that part so far, and then we will keep moving. Okay, what do we have in here? Schnellanruf. No, I'm not doing a Schnellanruf. Whoop. What's happening? Okay, good. Okay.
I have a request.
Yes, go, Sam.
Could we do torques?
Yes, we can do that. I think we can. Just
Thank
a
you.
minute. Okay, so I'm going to take pictures as we go along. All right. Boop. Okay. Okay. That was problem 1A and problem 1B. Now we're going to make it slide. And if it does slide, whoop, I'm going to I can do this pretty quickly. We've done this quite a bit, I think. So we have then that the downward force is mg sine theta, right? The upward force is ff. And then because it's kinetic friction, that will be mu k times Fn, which is mg cosine theta. There it is. And that whole thing is equal to ma. Okay, so what we're just doing here is sum of the forces equals ma. And this is picking up where we left off a second ago. For the motion, again, the m cancels. It only works if it actually has mass. Seems silly, but you could imagine like a massless object obviously wouldn't be attracted by the Earth. So that makes sense. So then A is already solved. We got that. It's g sine theta minus mu k. Let's do it this way. It's prettier. There you go. A is g times sine theta minus mu k cosine theta. And that's part C. Good. And cruising along. Okay. Oh, they're asking for us to explain stuff. Okay, let's just read through it. The incline is set with the angle theta. The angle is slowly increased until the block begins to slide down the incline. After the block begins to slide, the angle is kept constant. Until the block begins to slide, does the force of friction acting on the block increase, decrease, or remain the same as the angle increases? Okay, well, that's pretty straightforward. The friction force does what as you increase the angle?
Increase.
It increases, of course it does. Yep. And the reason for that being is that as we are in, oh, wait, I shouldn't explain this to you. Now, how would you justify that? It is true that FFS of theta, right, is an increasing function. So as theta goes up, FFS goes up as well. But why?
Because FFS is mu s g cosine theta, and cosine theta increases as theta increases.
Aha! You are trapped. And this is like, I don't want to be trapped. The exam is in 2 hours. Okay, so just a reminder, FFS is smaller or equal to mu s times Fn. Okay, so that means it's smaller or equal to mu s mg cosine theta. It is not equal to that value, actually, except for at the final point. That makes sense?
Yep.
Okay, and even worse, look at cosine theta. What happens to cosine theta as theta increases from 0 to a larger value?
It decreases and then increases. And
It
then
actually
decreases.
decreases. So if you were going to go based on this equation there, Giannis, it would be a trap that you would fall into, and then you'd have like in the pit of sadness. That makes sense?
Oh yeah.
So cosine theta decreases as theta increases. So this is a problem. So as theta increases, we want the static friction to increase, not decrease. Okay, but hey, we're safe because remember, while we're increasing the angle, right, our free body, our force equation looks like this. We have FGX downslope and we have FFS upslope, and this thing's equal to 0, right? So that means that as we're increasing the angle, FFS is equal to FGX, and that's of course equal to mg sine theta. Yeah? So as we increase theta, now looking at this relationship, FFS is equal to mg sine theta. So as we increase theta, sine theta increases up to an angle of 90 degrees, but that's silly. I mean, we're not going to increase the slope beyond 90 degrees. That's stupid, right? Because that's our angle theta, right? We can't go past 90. That's dumb. I mean, 90 is already, you're falling straight down. So there you go. So that means because FFS is equal to mg sine theta, while the block is not moving, and sine theta increases as theta increases, therefore the force of friction static increases as theta increases. Okay, Dennis, that feel better?
Mm-hmm.
Not to pick on you, but hey, it's cool. This is all difficult, so don't feel bad. I mean, that's why we're doing the course, right? Okay, if the block
Wait,
is slot.
essentially what you just went through was just that as the angle theta increases, the force of static friction also increases.
Yes, correct, and the justification.
Right. Okay, good.
Exactly.
Just
So this
make
was
sure.
part.
Wait, hold on. But there's like you have two different equations there, which are like,
The,
one is cosine theta and one is sine theta.
not two equations.
Oh, okay.
It's an inequality. Gotcha, buddy. Yeah, so it's an inequality over here, and they're both, this inequality holds and this equality also holds. So both of those are true. Yeah. Sorry, I got excited. Is this snorting too much? Okay. Sorry. Okay, so that was problem 2D1. And now let's move to part II, as some people like to call it. It's part 2, actually. This is part D2. Now, as the block slides down the incline, does the force of friction acting on the block increase, decrease, or remain the same? So I think what they mean, okay, is when you increase the angle, okay, once you get to the angle where it starts sliding, in that instant, jumping from static friction to the kinetic friction, has the friction force increased, decreased, or stayed the same as we jump from static friction to kinetic friction? That's the way I'm understanding the question, although I think their question is unclear. Okay, do you guys understand what I'm saying? Okay, I'll pretend you said yes. So we're going to ask the question, as it starts moving at an angle of theta max, just at that angle, static friction has reached its maximum value, and then the block starts sliding, and it's sliding down the slope against kinetic friction. Is that kinetic friction larger, smaller, or equal to the static friction? Good. Let's ask you, and first of all, has the friction in that instant gone up, down, or stayed the same?
Down.
Down. It has down, exactly. So we have that as it starts slipping, so FFK at theta max needs to be less than FFS at theta max. Good. Now, let's get an explanation for that. Why is that the case?
Mu k is always less than mu s.
Good. So I think there's two ways of explaining this, and I think you're absolutely right. And FFK is, of course, equal to mu k mg cosine theta max. And over here we have mu s mg cosine theta max. Okay, that's true. In this case, it's equal to the inequality because we're looking at the maximum angle. And of course, you can then say, okay, because mu k is always smaller than mu s, and everything else cancels out in the equation, as long as they're not 0, right? M's cancel, G's cancel, cosine theta cancels. Therefore, because mu k is smaller than mu s always for every situation, as we've been taught by our physics teacher, we're good, and that's a justification for why this is true. Now, there's another justification that I actually like a little bit better. and it's actually in the description of the problem, because we said we've increased the angle, right? And we've gotten to the point of theta max, and at theta max, the block starts sliding. In order for it to slide, what must be true of the block at that point? Anybody?
That the force of friction is smaller than the component of gravity that is pulling it down.
Yeah. I'm gonna give you a little hint here. Is that true? Like initially it's not moving and then it's moving, right? What is happening here for that to be true?
There's an acceleration.
There must be an acceleration, right? There is an acceleration that's greater than 0. And what must be true, therefore, is that when we compare mg cosine theta, right? Mg sine theta, and we compare it to FS, earlier we said those are equal to each other, right? Because it was holding it without letting it accelerate. Now, if we compare mg sine theta with FFK, right? Because it's accelerating, what must be true? What kind of sign should I put between them in order for that to work?
The mg sine theta is greater.
Exactly. So this is greater than FFK. So that means because these are equal to each other and this one's greater than this, that means that FFK has to be smaller than FFS. And I like that explanation. And it kind of, but I think they would accept both.
Wait, how is that different from my explanation?
I don't think it necessarily is. Did I tell you you were wrong?
I thought you did. Maybe I misunderstood.
Okay.
I mean, I think what I meant is that like the force of friction has to be smaller than the component of gravitational force that's pulling it down.
Okay,
That
then that's exactly correct.
Okay.
Mr. Blessman,
Yes.
I
ma'am.
understand your approach, but I understood the question differently and chose
Okay.
remains the same, arguing that the force of kinetic friction remains the same while it slides down.
Oh, okay.
Kind of the other version you were
If the
talking
block
about.
is sliding down the incline, does the force of friction act? Let's see what they thought about what they meant. You can kind of, in retrospect, be like, question writer, what were you thinking? Let's see. Damn it, Janet. I think you're right. That's what they meant. If the block is sliding down the incline, does the force of friction action on the block increase, decrease, or remain the same? Okay. So, Hannah, you're right. That's the way the question writer is asking the question. I think that's kind of a silly question, right? Because we've been told that it's especially silly when you look at part E, I think, because in part E, they're saying it's not constant. Like, what? What just happened? Okay, so
Yeah.
force of friction, kinetic, is velocity independent. It does not depend on velocity. It's at the same friction force at any speed. Therefore, even though it starts sliding and it's accelerating, that should not affect the value.
I'm confused about their justification.
Oh, let me see.
I'm confused about what the difference in is. Did we just do the wrong thing?
Well-
I think the question was ambivalent. No, ambiguous. Ambivalence means something different. Ambiguous. So it's an ambiguous question. So because it could be a time dependence as it's sliding down the incline. That's what they meant, I think. Or you could say, what's true of the, at that instant, as it starts to slide, right after it starts sliding, is the force of friction lower. So what that means is, let's kind of summarize this. If we did this as a time experiment, okay, the force of friction, and we're kind of going to increase the angle at a rather constant rate, then it's going to go up, right? Oopsie, can't see it. Yeah, and then it's going to dip down and stay constant. Good. So this is like FFS right here. this is FFK, right? This part, colors will be so good at this point. So let's switch this to red. So this is the kinetic friction. That's the static friction. And then this is the transition.
Are we graphing this versus time?
I'm just saying if we, yes, correct. If we were to slowly increase the angle, static friction would increase until you reach theta max, and then it would dip down and go across. So I think when they're comparing frictions, I interpret it, the question is saying, is there a dip down here, right? What happens right in this instant? And they were saying, I'm interested in the red part, but both of those are really once it starts sliding, because the sliding process starts here and then continues here. So that's why I think they're two different answers. Let's see what
Wait,
they
could you
got.
reread the question?
Sure. If the block is sliding down the incline, does the force of friction acting on the block increase, decrease, or remain the same?
But I thought the force of friction is dependent only on the friction coefficient and the normal force.
Correct.
Right, so why is there a dip down and why would it change over time?
Cool. So because the transition occurs between static friction and kinetic friction. So this case, the block has not slipped, 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 has not slipped. Okay, then when it starts slipping, the friction force dips down because it transitions to kinetic friction. And then it accelerates down the slope at a constant friction force and a constant acceleration. That's how this should work.
The idea is that it's easier to move something once it's already moving.
Correct. So the idea being, because mu k is smaller than mu s, therefore the friction force here, the kinetic friction, has a value that is lower than the maximum value for the static friction force. Let's see what they explain here and how this makes sense, if it does make sense.
So the friction coefficient of static and kinetic friction are just different numbers. That's what makes the difference?
Yes.
What? This justification makes no sense.
Exactly. I don't understand.
Whoa! This is really shitty. Sorry. Yeah, that's definitely the wrong explanation for this situation. So there's a third option apparently, that they didn't apparently. So if you were, whoa, okay. They said they stopped increasing the angle once it starts sliding. Didn't they say that in the problem?
Yeah.
Okay, so you could be like a crazy person and make the angle keep increasing when it's already sliding, right?
Mhm.
And that's actually an interesting question to say, what happens to the kinetic friction then? And of course, the kinetic friction in that case is decreasing, okay? So, but that's not the answer they have. So their justification goes with a different answer. So that's definitely wrong. So two ways to interpret this question. They didn't choose either one of those. They definitely screwed this up. They should have clarified this, but we can explain the physics. As we increase the angle, the static friction reaches a maximum value. At theta max, the maximum value is reached, and then once it starts sliding, it's no longer static friction, and the value of the friction has dropped because mu k is smaller than mu s, and we can also say it's accelerating now, so it must be smaller. And then it slides down the incline at an acceleration, and the constant kinetic friction is reducing the acceleration below mg sine theta, but it's a constant reduction. But during this phase, kinetic friction is constant, but kinetic friction is lower than the maximum value of the static friction.
Okay.
Okay, so that's a good explanation. That's definitely correct physics. I don't know what they're doing. They might have been like smoking crack or something.
And I mean, they say that the angle stays constant after it slides. So I could include that, right? Because.
Yeah.
Okay.
And I'm 94% sure that the quality of question tonight's better. Okay. Some bad questions have made it through, but that's a bad mistake, right? Because that should come, I mean, that should be shown like on the first proofread that that's wrong. So, and E is actually not that great a question either. Sammy sent me a message about that yesterday, asking about it. And it then says, well, guess what? It's now sliding, but actually our friction force is not constant. Oh, guess what? Surprise. So we're going to have a friction force that depends on how fast the object is moving. Okay? That is unrealistic. So I'm going to rephrase the question in a way that makes sense. Okay? So we're going to say we are at the maximum angle at which this thing would start sliding. It has to start sliding. And now this thing accelerates down the slope like a skier down a slope. Okay, so imagine the block is not a block on a table because it's not really moving very fast. We're going to think about a skier getting faster and faster, and the skier's getting faster and faster to a degree that actually friction force is not that important anymore, and air resistance becomes more important. Okay? Now we're making this into an AP Physics C problem at that point, because up to now everything is AP Physics 1, honestly. Okay? So at that point, once we're saying, whoa, what happens if the thing is moving so fast that air resistance becomes way bigger than the friction force, okay? And how can we think about the problem then? Okay, did I take a picture of this already? I did, so this is good enough. I'll erase this. Sometimes they do that, where they take the problem on part E and are like, crap, we need some calculus, okay? So now we're going to make this thing be a skier, right? Oh, this is not good skiing position. That guy has an arm coming out of his thigh. That's bad. Okay, so here, that's not good either. But let's just imagine, here's a skier, okay? That's not good position, but whatever. Okay, so you're moving. Okay, so now we're saying the following. We have still mg. We have still Fn. Okay, but we get to the point where the friction force, air resistance force is much bigger than the friction force, so we can just kind of ignore that. This is probably true for like downhill skiers who are going so fast, like 200 kilometers per hour, so kind of like that. Okay, imagine that. So your air resistance force at that point is actually much bigger than your friction force, especially because the coefficient of friction between skis with wax and snow is very low. Okay, so we've switched this idea to, we're replacing friction force with air resistance. Now it makes sense that air resistance force, right? Air resistance force does depend on velocity. Okay, the faster you go, the more air resistance there is. And generally, it's true that this is really of this form. Okay, minus kv squared. So and minus means against the motion, and there's a constant involved here. And then there's normally dependence on v squared. But in our case here in the problem, and generally what we do in AP Physics C to make the math easier to do, we say, okay, this is too hard mathematically to do the separation of variable process. We're not going to use that. We're going to say, assume it's something like c times v. Some constant times the velocity. So at least we have that factored in, that it matters how fast you're moving, okay? And if that's the case, all right, so now we're ignoring friction and just saying air resistance is what matters. So we can think about what's gonna happen to the guy as he accelerates down the slope. Okay, initially has, of course, no speed and gets faster, okay? And initially, what is the acceleration the skier experiences?
mg sine theta.
Mg sine theta, exactly. Mg sine theta is the force, and initially air resistance is 0, so the acceleration is g sine theta. So if you had have a slope here, oops, right, where this slope equals g sine theta. Make sense? Initially, the skier kind of is close to this. Make sense? Second question, what happens later. Eventually, the skier is going so fast that the air resistance is preventing him from accelerating anymore. We call that his
Terminal velocity.
terminal velocity. So eventually, he'll reach a zero acceleration. How will we signify zero acceleration on a v versus t graph?
Constant v.
Constant v, good. So a horizontal line. This is v terminal. Good. So that he starts this way, and then he kind of asymptotically approaches this value. So that makes sense? And looking at this, you're like, ooh, capacitor charging, right? Yes? Yeah, you thinking that? So it's some kind of flipped negative exponential, right?
Mm-hmm.
Makes sense? That's what it is. And if you solve the equation that you would get from this here, that's what you would have. Okay, so you'd have, if you take the Newton's second law, oh crap, I didn't just leave enough room, and now I'm making a mess with my hand. That's not cool. Mg sine theta minus CV equals M. And now, if they asked us to make this into a differential equation, then we shouldn't write A here, right? Because a differential equation always has to have a function and a derivative of that function, okay? And over here we have V, so here we should write dv dt. Make sense? Okay,
Mm-hmm.
and this, if you solve this, we actually did this in class, you get exactly this kind of, the same kind of function as you would get for a charging capacitor. Good, but that would be the equation to write down. A couple things here that we, just to finish this problem specifically, they then ask, well, what's true of the acceleration? Okay, well, the acceleration starts out at a non-infinite value, right? So I could mark here g sine theta. Okay, oh, sorry. What I meant to do is, this is the A versus T graph, the V versus T graph. And of course, it then goes like this. Whoa, and it doesn't go back up, Doodle, come on. There we go. Okay, make sense? So those are your two A versus T and V versus T graphs. Make sense? Cool. And that's also an exponential, yeah? Of course, and they're related, yeah? The derivative of an exponential is also an exponential, that's why that makes sense. Negative exponential, this is flipped negative exponential. Okay? You guys happy with that problem?
Yeah.
Okay, good. I'm kind of glad we talked about it. I thought there was not much here, but I think we got some meaty stuff out of it after all. So that's cool. Okay. Ooh, cool. Looks like problem 3 is specifically about a skier. Interesting. So Sam, you said you wanted to talk about torque. Can you be more specific on what you're interested in doing?
Well, hold on. Like rotational inertia, I guess. And like rotational like kinetic energy, stuff like that.
Okay, we can do a little review on that.
Thank you.
So the big thing there is for you to remember that you need to make the transition from linear to rotational and keep that in mind. So how are the two concepts related? Because if you can deal with the linear, then you can deal with the rotational, okay? So always important to keep in mind the relationship. So if you have linear quantities and rotational quantities, x is theta, v is omega, a is alpha, p is L, m is I, F is torque. Okay, I'm kind of out of space down there a little bit. Okay, that's important. And the other things you need to consider is that there are connecting, so there's linkage between these two. Okay, so for example, the distance around an arc is theta r, right? The velocity, the tangential velocity of a point, something is rotating omega at a distance r is omega r. The acceleration, same idea there, oopsie, is a equals alpha r. So you can connect those together. Those are important. And then, of course, they're also important equations to remember. And what I mean by that is, whatever equation works over here also works over there. And you have them on the sheet, but at the same time, it's always nice to kind of remind yourself of that. So m, well, that's just I, so replace that, okay? And v is just omega, so there you go. There you go. So L is I omega. And so here it comes to the question, okay, so F, torque. So torque is R cross F, okay? All right, whoopsie, let's go down here. There we go. So, and that means, of course, the magnitude of torque is R F sine theta. Good. Now coming back to this, there's a few things you need to kind of remember about this here. So first of all, for a point mass, right, I is just equal to mr squared. And r is the distance to the point of about which you're rotating. That's the first thing. If you have a distribution of mass, okay, in theory, we could ask you to find that by doing an integral over the volume of r squared dm. Okay, under the best of circumstances, this leads to disaster among students. Under the current circumstances, they're not going to ask that. If they do ask that, it's going to be just awful. So don't worry about it. If that's going to happen, if they actually say, derive the moment of inertia of a linear rod about its center of mass, show all your work, and then you're supposed to type everything. I mean, come on, give me a break. It's stupid. So that's not going to happen tonight. But what could happen tonight is that they could ask about the parallel axis theorem, okay, in terms of this. And what that says is, if you know the moment of inertia about the center of mass, okay, so for example, the example I said, right, I said if you know the moment of inertia of a rod like this, okay, and you're gonna spin it like this, right? And I think it's 1/12 ml squared. I'm pretty sure. This is L, and this is M. Okay, so moment of inertia about the center of mass is, I think, 1/12 ml squared. You can do that with calculus. Okay, now you might also want to ask, well, I don't want to do that. I want to use this kind of like a baseball bat. So instead of using it here as this is my center of mass axis, I want to know its moment of inertia about this parallel axis. Yeah, so about this parallel axis, this thing has more inertia because on average the masses are further away. I think that's intuitive, yes? That it's because the mass is on average further away from the point of rotation. That is a bigger moment of inertia. And the equation for this is that the moment of inertia about a parallel axis is equal to the moment of inertia about the center of mass axis plus, ooh, colors, I like colors, plus m, and then do r squared, where r is the distance between the parallel axes. Okay.
Yeah, I understand that, but how I'm talking like, okay, what I'm doing is like I just like reviewed a lot of like basically all the units and all of mechanics, and like I'm just on the last unit. I kind of wanted to like speed it up. So yeah, I just learned about like the whole like what's it called again? Inertia, rotational inertia thing.
Cool.
And axis theorem. But like I'm like still a bit confused about like conservation of like
Energy?
no,
Momentum?
yeah, rotational momentum
Okay.
or energy and stuff like that. Like
Sure.
I'm having trouble visualizing how like you conserve that. You know,
Okay.
like there's no like collisions. You know, it's like
Oh,
it's
cool.
different.
They are collisions. And that's one of those things about what a collision is. Okay. A collision is a situation where the internal force is 0 to the system, or where the internal torque is 0 for the system. And the examples that I have that you guys tend to not think about as collisions are like a rocket, right? That is flying through space. Okay. And we're just going to blow this thing up. There's like explosive in there, right? And then the pieces 1 and 2 will have different momenta afterwards. Okay. But the total momentum of the rocket pieces compared to the momentum of the rocket would be conserved. And this is in certain ways similar to a ice skater spinning and pulling her arms in while she's spinning, or a person on a merry-go-round, one of those playground carousels, yeah, walking in or walking out on the carousel, on the merry-go-round. In that situation, it doesn't feel like a collision, right? But it's a situation where the internal forces or internal torques are the only ones that matter, because the external forces are 0 or negligible. So for this situation, we say the internal forces of 1 pushing on 2, 2 pushing on 1, are so much bigger than the gravitational force of the Earth or air resistance or whatever, that we can just consider the internal forces the only ones that matter. Same situation. What's that, Micah?
Why is there no distinction made within like rotational kinematics between rotational impulse and rotational momentum?
There is. Okay, so the
Because
two
I
words.
don't have an equation for a
Sure.
rotational impulse
There
on
is.
my.
Hang on. There is. So let me just finish the sentence, and then I'll get to that question. Okay. So for the rotational situation, the merry-go-round person walking exerts a lot of force. Technically, there's an external torque due to air resistance and or the axle having like friction, but we're ignoring those, and the overall momentum, angular momentum in this case, would be conserved. So we call that a collision as physicists because we're weird. Okay, similar to pushing 2 carts together and then releasing them, and they move apart because there was a spring between them. That's also a collision. Okay, in that case, momentum is conserved. To answer
Okay,
Marcus,
but hold on. Okay, sorry, but why is it rotational and momentum then? If it's an explosion like that, like why is it?
No, this is not. This is linear momentum. I'm giving this
Yeah,
as
but
an
I'm talking about.
explanation to the other one.
Okay, but what is rotational momentum?
Angular momentum is conserved here too, but it's not useful.
Okay. When is there a situation with like angular momentum?
I just described one. So you have a merry-go-round, and you have a
sorry.
person on the merry-go-round, right? I'll draw it over here. You've got your merry-go-round, it's spinning. Whoop. Here's your kid on the edge. It's rotating, okay? And then as it's rotating, the kid walks towards the center, okay? Angular momentum will be conserved, okay? Which means the overall thingamajigger will speed up, right? Similar to ice dancer pulling her arms in order to spin faster.
Right.
Same idea there. Okay, hang on. Let me get back to Malka's question. I'm actually super happy you asked that. Hang on a second. I think you asked about just momentum, okay, and impulse. So those 2 words are really important, okay? It's kind of coming back to a different question. So impulse is J, and J causes momentum to change, okay? And impulse specifically, what that is, it is a sum of how much force you've exerted over time on the object. So if you exert force for a time and you integrate that or add it up as a function of time, that's how much impulse you've given to the object or the system. And that impulse will change the momentum of the system. Okay? this is conservation of momentum if the external force is 0, because this is just the external forces on the system. So that's important to note. This is external, only works if external. That's the impulse. Okay, and the same thing is true for, and this is what I love many things about physics, obviously, but you can also talk about, oopsie, didn't mean to write a K. You can also exert force over a distance, and this is now a dot product. You will get out a scalar, a number. You do work by integrating F over X. And this is the change in kinetic energy. And ain't that pretty? You have a perfect parallelism between
So how do you calculate
impulse
rotation?
changing momentum and work changing kinetic energy. Monica, go.
So how do you calculate rotational impulse then? Just the torque over time? Like
Yeah.
the torque
Yes.
integrated over
Yes.
time?
Yes.
Okay.
Yep. Yeah. Genau. So these are linear concepts, but the vertical the rotational concepts would apply there too. So yeah. So torque applied over time would be rotational impulse, which would be delta L. There's no letter for, I think, on the sheet for, and even some equation sheets don't even list a letter for impulse. It's not as common to use this letter, but it's still true, right? That integral torque dt is equal to delta L. That's true. Integral torque dt equals delta L. Whoa. Take a picture of that. There we go. Okay, is there, well, I don't know how you feel about it, but looking at the two equations, the two sheets I have here for the two problems that we still haven't talked about out of that set, maybe because we introduced F versus T, hello, maybe we should talk about this one, okay? Unit 4, which has an F versus T graph, okay? And that's a momentum problem. Yes?
Sounds good.
Sounds good. Do you guys need a pep talk? You seem sad. Okay, here comes a pep talk. You're good enough, you're smart enough, and gosh darn it, people like you. I can make it longer. You guys are working hard. You're gonna go do a great job tonight. It's gonna be awesome, okay? So just make sure you drink enough coffee and don't fall asleep during the exam.
Thank you.
Okay, Hannah's like, that was semi-inspirational. I've had better pep talks. I really think you guys are gonna rock it tonight. I really do. I'm not just saying that because I'm supposed to. I really think you're gonna be awesome. I really think you are. Okay. Let's take a look at Unit 4, progress check. So this is Unit 4 now. They've given us some kind of diagram that looks like this, F versus T, and it starts at about 3. Four, and it goes up to about 6. There we go. It goes from 3 to 6, 5, and that is at 12 seconds. 3, 6, 9, 12. Here, and then here. That's like that. Okay, close enough. This is 2, 4, 6, 8. Who do we appreciate? There we go. Oh, shiitake mushrooms. Sorry. That's not good. So 3, 6, 9, 12. Who do we smell? Okay, good. There we go. All right. Good. Now they also give us the final speed over here. They say up here, speed is 1.5 meters per second. And they do tell us that, oh, cool. Cool, cool. And do they start it from rest? Does it say that? Okay, yes. Here, V0 equals 0. Good. Make sense? Okay. Is this too easy for you guys? Are you guys still there?
Yeah, still here.
Still there. Did you do the problem already, or is it too easy or too hard, or are you just sad? I can do another pep talk. No,
I think it's a good review. I did already, but still.
it's still a good review. Okay, good. All right. Cool. So let's take a look. We have here our F function, right? So F of 0 is 3 newtons. Then F of 6 is equal to, sorry, F of 12 is 6 newtons. Good. All right. So let's take a look. We can definitely find the total impulse. That's good stuff, right? So let's take a look. We can say, okay, we can either remember how to find the area of a, whatever this thing is called. Don't know what it's called, but it doesn't matter. This rectangle, 3 times 12, that's 36 Newton seconds. Makes sense. 3 times 12. Speeding up a little bit to make it more interesting. Then we have 3 times 12 divided by 2, so this is 18 Newton seconds. And of course, that means that the total impulse is equal to 54 Newton seconds. Okay, and we also know that that's equal to delta P. Okay, 54 Newton seconds equals mass times V minus V0. And we know those velocities because they were given to us. So 54 Newton seconds equals M 1.5 minus 0. Okay, so that would mean, of course, that M equals 54 divided by 1.5, which is 108 divided by 3, which is 36. 36. That is a very, very massive block. I mean, cart or whatever they're doing. Okay, they've got heavy objects apparently. Yeah, that's correct, I would think. Okay, and that answers questions 1, 2, 3. A1, A2, and B. Okay, so A1 says we talked about it. How would we find the answer? Yeah, because we are using the fact that impulse is equal to delta P, and we could describe that. And that's definitely fair game for tonight. I think them actually asking you to find all this, I don't know, this actually seems reasonable. I think you can do this on typing it up, right? Like 54 divided by 16 equals 36. That's not like overly typey. But again, I think they're going to have more explaining stuff tonight. So that gets us through answers A and B. C, good. When T is 12, the force sensor loses contact with the block, which continues to move along the horizontal surface. When T equals 20 seconds, the block encounters a rough area and comes to rest in 25 centimeters. Oh, come on, people. All right. Somebody left a glue gun on. What's wrong with these kids? Okay. Okay. All right. Sorry. Move along. Block encounters a rough area and comes to rest in 25 centimeters. Cool. Cool, cool, cool. On the graph below, sketch a graph of the speed of the block as a function of time. Okay, so let's just repeat. We pull this thing, and are we pulling it with a constant force for the first 12 seconds? Don't be shy.
No.
No, not a constant force. Is the force increasing?
Yes.
Yes. If the force is increasing, what must be true of the speed of the object? Not only is it increasing,
Accelerating.
but it's increasing at an increasing rate. Capiche?
Its acceleration is increasing.
Its acceleration is increasing. The third derivative is greater than 0 of the position, or the second derivative of the velocity is positive. Make sense?
Yeah.
Okay, so how do we express that? That would mean that at the start, I'm limited on space. Sorry about that. So we have kind of here the V graph. We have our 3 zones. Okay, but we start at what velocity? They told us it starts at the velocity of
0.
0. So it starts here, and then it reaches 1.5, which is here. Oh, let's actually make it higher. 1.5, which is there, right? Which is the speed at the end. So it gets there. How does it get from there to there? Straight line?
No.
No.
Concave up.
It needs to be like parabolic upward, right? Because it needs to be increasing at an increasing rate. But technically, it can't be parabolic because that would be a 0 acceleration at the beginning, and that's not true. So it'd be kind of like this. That cool? Make sense?
Yep.
Yeah.
Okay. And at that point, they say, oh, it's going to lose contact, and now it's just cruising, right? And we're going to ignore any kind of friction after that point or anything like that. So between these 2 times, there's no net force acting on it, and therefore what should be true of the V?
It's constant.
It's constant, so it'll be moving it straight across. Okay, and now it's going to hit the rough patch, right, and come to a stop. And as it comes to a stop, the rough patch is exerting a friction. Is the friction force that the rough patch is exerting on the block velocity dependent or not velocity dependent?
Not velocity.
Not
dependent.
velocity dependent. So this is not some kind of weird friction. So it should be a constant deceleration. So our line should go from here down to our 0 value in a straight line or not straight line?
Straight.
Straight line, correct. There we go. There we go. And we've sketched it out. Yay! And they couldn't ask you this, I think, like this. They could ask you to describe it, or they could give you different graphs. They could do that, right? Like they could be like, give you 3 different shapes, right? Or 4, and say, pick which one it is and explain why this shape is correct, right? So that's possible on tonight's test. I think just graphing this, drawing this is going to be too hard. Okay, let's see. Let's do it again. Blah, blah. Rough speed. Yeah. Calculate the kinetic friction. Coefficient of kinetic friction between the block and the rough surface. All right. Okay, comes to rest in 25 centimeters. Oh, I love this. Oh, sorry, that really excited. So they tell you that at the end, it takes 25 centimeters to stop. 25 centimeters to stop. If you have a distance that a force is acting, that should indicate to you that what approach should you be using here?
Energy.
Energy, because exactly, work and energy, because time dependence of force, you're looking at impulse, right? And momentum change. A distance relationship, how much force is acting over a certain distance, is indicating that we're looking at a work energy situation. Okay.
So since the acceleration is positive, could you also use kinematics?
Yes.
I mean constant.
The acceleration is negative.
I meant to say constant.
Is constant. Yes, you could. That would also work. Yep. I have a feeling that friction and going directly to work is going to be faster, but I'm not sure.
Sorry, I don't know if Sam just asked this, but couldn't one use like simple mechanics?
I think you mean the same thing. It will be kinematics, and we can. Oh, are we nerdy enough to solve it both ways?
Yes.
Yeah, of course we are. Hello, let's go. Okay, so let's see what we have, and we'll go with Sam's suggestion first, because he said, can't we just use kinematics? We know V0 is 1.5 meters per second. We know V is 0 at the end of the process. We know that x minus x0 equals 0.25 meters. Great.
Mm-hmm.
Good. So we can use those 3 very easily to find A, right? Because we have V squared equals V0 squared plus 2A x minus x0. Good. So we can find A is equal to V squared minus V0 squared divided by 2x minus x0. That pen writes beautifully. I like it. So Minus V0 squared is 2.25. Again, we're leaving the units off, a little easier to do it that way. And then the bottom, we have 0.5, 2 times 0.5 here, 0.25 meters, yeah, it's 0.5. There we go. And that means we have an acceleration of minus 0.5 meters per second squared. Yeah, makes sense? And then, of course, that means we can find easily the force that's acting, and that's the friction force, right? The friction force is equal to this acceleration. It's the only, times the mass of the block, because that's the only force that's acting on the block while it's skidding across that sandpaper. So that would be mass of 36, so it's 36 times minus 4.5. It's to the left, but we're just looking at the magnitude, right? Let's do it this way. So 36 times 4.5, 120, 144, plus 18 is 162. So 162 newtons is the force. Is that correct? Yep, that's right. 162 newtons. All good? Okay. So if that's true, this is a kinetic friction. Kinetic friction is equal to mu k times Fn, right? Which of course equals mu k times the normal force, the horizontal surface, so it's just the mass times 10. So it should be 360 equals 162. And we leave a little room over here to find the answer. So mu k is equal to 162 divided by 360.
That's 0.45.
0.45. All right, good. Let's take a picture of that. Okay. All right, let's make a little room in the middle here for the, this is a good problem. I like this problem. I think it's good. Combines a lot of concepts. There we go, middle. And we said that work is equal to the change in kinetic energy. Okay, and the work is of course done by the force of friction times how far you're sliding, right? And the change in kinetic energy, I'm dropping the sign, I'm being a little sloppy here, but there you go. Okay, makes sense? So the friction force is reducing the kinetic energy by this amount by acting over a distance delta x. Make sense?
Mm-hmm.
Okay, and then force of friction, of course, we can say, okay, well, that's mu k mg times delta x, 1/2 m v0 squared. Good. And then we can do a little cancel-oo. Say, we'll make the m's go away. Mass has to be 0 again, otherwise this won't work, but it cannot be 0, sorry. Okay, there we go. And we can then go up here and say, okay, mu k is equal to v0 squared divided by 2g delta x, 2g delta x. Okay, is that correct? I think it is. Okay, so we got 1.5 squared divided by 2 times 10 times 0.25. There we go. And this is 0.45. It is actually. So that's through work, and not surprisingly, work and kinetic energy gets you the same result as the kinematics approach / Newton's laws approach down here. I liked the friction, using the friction in the work a little bit more. Thought it was a little bit more straightforward and easier to get to, but either approach would work, obviously, in this case. So don't feel bad if you had instincts one way or another. Either approach shall work. I'll take a picture of that too and send that to you. All righty. And that's the kinetic friction. The students repeat the experiment with a block that has twice the mass of the original block. The students exert the same average force to the block. The students again get the block to move with a speed of 1.5 meters per second. Okay, interesting. Same average force. Oh, they're being really awkward here. Okay, fine. So let's be specific here. So on this process, they were exerting 4.5 newtons on average. Okay, so now they're going to exert 4.5 newtons on a second block that has twice the mass. Okay, and we want to get it to go at the same speed. Okay, so what is true of the time necessary to make that happen? That's the question they're asking, right? Which of the following, well, they give you options, isn't that nice? All right. So, so what's the deal? Will it take longer? Yes. Okay. Before it took 12 seconds to get there, right? How about now? Well, let's think about it. We have a mass that's now increased to, was it 36 before? Yes. So now we have 72 kilos. So it's times 2, right? We want to be V the same, 1.5 meters per second. So what needs to be true in terms of the overall, why is this, why are they giving you a range? This is stupid. Am I missing something? So we're getting to the same speed, but we're having twice the mass. So how much change in momentum do we have now in this second situation compared to our first situation? Twice the mass, same velocity change. Okay, I'm just going to say it. It's just twice. It's simple, right? Agreed? Yeah? And if it's twice the impulse, if it's twice the momentum change, that means that our new impulse needs to be twice the previous impulse, right? Oh shit, it's not on the screen there. There we go. But impulse is just force integrated over time, or you can say it's force average times time, and the force average is the same. They're saying we're using the same average force now, right, as we did before, right? Well, that just means that the time's going to be twice as long. Am I wrong?
No, you're right. They just want you to say it's over 20 seconds.
Okay, that's stupid. It's twice as long, so it should be 24 seconds. Okay, I'm not sure where they're being complicated. Yeah, it's twice the mass, should be twice the momentum change, twice the impulse. If it's the same force on average, then it's going to take twice as much time. Yeah, they don't know where they're doing that. Holy cow, they got 5 inequalities written down. How stupid is that? That's really weird, isn't it? Like, why would you do that? I mean, it's a straightforward problem, right? Just twice. Anywho, okay, last one. Assuming the new block reaches the rough surface with a speed of 1.5, is the distance it moves in coming to rest greater than, less than, or equal to the distance? Okay? So, looking at what we did, notice how prominently the mass featured in those equations. It didn't. It canceled out, so it doesn't matter. Should be the same. Okay, because the friction force is proportional to the mass, and the kinetic energy is proportional to the mass. The work done is proportional to the mass. Everything's proportional to the mass. Therefore, in this situation, the mass does not matter as long as it's not 0. Then we're all good, and therefore, we even said that, right? Mass can't be 0. You can cancel it out. So no difference, should be the same because it cancels out in everything. All righty, we got through that as well. Whew. Everybody still having a good time, or should we call it quits, or are you guys okay? Still breathing?
Yeah.
Mr. Blessman, I've
Yeah, Luai.
got a question.
Yes, please.
Why do capacitors in series have the same charge?
Oh, okay, cool. That's a great question. So we've got a setup like this. Okay, we've got some EMF. We're going to close the switch. Let's see what happens. Okay, this thing is an electron pump. Okay, and it has a tendency to take electrons and take one electron from here and be like, whoop, push it over there. That's what it does. Okay, so when it does that, it's going to take an electron off this side, making it positively charged, right? I'm going to make it bigger because it's not showing up very well. This one bigger too. Okay, makes sense? So this is an electron hole, a holy electron. So there's plus there, eh? Makes sense? And then of course this electron goes, hello, I'm down here now. Make sense? And of course that electron up here, the positive charge over here, would have the tendency to attract an electron over to locate at that position as well. The same thing happens here then, that here would be a positive charge because an electron wanders over here and deposits itself there. Okay? And that happens for every single electron that does that. And there's no other way this can work because these two are isolated, right? There's the total charge of these guys needs to be the same, right? So this is going to be a negative charge here, minus Q in this one. And this charge has to be plus Q, and those have to be equal to each other because the total charge of these inner plates is 0 because they were initially uncharged, and therefore eventually they'll still be uncharged in total. So the total charge has to be 0. And of course, that means that, okay, well, these have the same charge and these guys have the same charge too. So we talk about the charge of the capacitor, and you know, technically the charge of the capacitor is still 0, right? Because plus Q and minus Q are just a charge separation. The total charge is 0, but we just say it's Q for the charge of the capacitor in terms of saying how much charge is on the positive plate. Okay, but that's the same here in terms of just signs being different. Same thing here, and then same thing down here. That work, Luai?
Yeah, that's good. Thanks.
Good, cool. And then of course, related to that, Q is delta V times C, right? Is related to this as well. The shopping equation is important in this context. And also that the total capacitance of this situation is equal to the inverses. This is something that's unfamiliar to you guys to some degree because for resistors, you're used to seeing this the other way around. Okay, here the charges are the same, but the voltage drops are different. So in this case, for this circuit, it would be true that epsilon is this total drop over here, or call this delta V, the total. That's equal to the sum of the two delta V1 plus delta V2. Okay, because it depends on the capacitance, right? Because the charges are the same, right? The charges are the same, Q, but the delta V's can be different because the C's are different, right? Because you can say it this way, delta V1 C1 equals delta V2 C2, right? Makes sense because if Q is the same for both of them, well, that means that delta V1 C1 equals delta V2 times C2. So the bigger capacitance has the lower voltage drop, and the lower capacitance has the larger voltage drop. Okay? And should I do it for parallel too?
Yes, please.
Okay, good. So we set the same thing up. Okay, I'll do it this way. I'll take a picture, send it, and then I'll erase it. I've got kind of a, no, maybe not, maybe not, maybe not, maybe yes. Okay. So we're now going to go over here. So, I'm not blue, I want black. With black. What's going on here? Come on. There we go. All right. C2, C1. So there you go. So again, the same idea, you close the switch, the pump's gonna move an electron. Oh shit, you can't see anything here. There we go. Voila. So electrons get pumped over here. That means relieving holes here, okay? And then we add those electrons down here, okay? So we pile from over here. Of course, they can go the other way too. It doesn't really matter, but the idea is that, okay, we get positive charges here and then negative charges here, fine. And certainly it's true that the total charge on top equals the negative of the, so the negative charges down here, they have the same negative amount as the positive charges in total up here, okay? That's true, but it doesn't necessarily true they have to be the same. And you can kind of conceptualize that by saying, well, if we imagine this pump, like trying to pump up two balloons that are connected in parallel, one of them might be a gigantic balloon and one might be a small balloon. Of course, it's going to be easier to get the charges into the gigantic balloon. So we're going to pile more charges in there. That makes sense. So if C1 is bigger than C2, C1 will end up with more charge. And let's actually look at the voltage to make sense of this. So initially, we'll have current flowing through the resistor, but eventually we reach steady state and no more charge is flowing. If no charge is flowing, then there is no voltage drop across the resistor and all the voltage drops across our capacitors. And of course, if you think about this like a skier, this is the top of the hill, this is the bottom of the hill. Each capacitor connects the top of the hill to the bottom of the hill. Therefore, the voltage drop across the left capacitor has to be equal to the voltage drop across the right capacitor. So in a parallel setup like this, it's true that delta V1 is equal to delta V2. And of course, if there's no voltage drop across the resistance, this voltage drop across each of the capacitors is also the same as the total voltage drop. Okay, so the voltage drop is the same that's provided by our battery or power source over here is equal to the voltage drop across each of our capacitors. Okay, and of course, in turn, because these are the same, delta V1 equals delta V2. We can take this equation if you want to think about the same way we did it just a second ago. Delta V1 is equal to Q1 over C1, and delta V2 is equal to Q2 over C2. Well, those two things are equal to each other. That means Q1 over C1 is equal to Q2 over C2. And that means that the bigger capacitor proportionally has bigger amount of charge. So if one capacitor is twice as big as the other, it contains twice as much charge. This is intuitive in this case, and that is the way it works out. And again, it is because voltage drop across the two capacitors is the same. Okay, and good. How are you guys doing?
Fine.
Fine, just make it end. All right, what do you guys need? Another pep talk? So let's just quickly review what's going to happen tonight and make sure everybody is, relaxed. The most important thing is to trust yourself. Okay, you've put in a lot of time. Some of you've put in even more time than others, but you've all been in this course and you've paid good attention most of the time and worked hard and all that stuff. So trust that you can do this. And the one thing you have to avoid is panic. So don't freak out. It's a short time for each of the questions. So try to calm yourself, whatever you need, like have some like birds chirping music or something playing. I don't know if that's allowed, but you get the idea. Whatever you need to calm down and just trust yourself and relax and be able to function. Because if you panic on a 15-minute question, it's going to be over. So don't panic about don't panicking though. That's not good either. So, you know, figure it out, trust yourself, you know some physics, figure out how to get points. You can't do part B and you think you're stupid, don't like throw your laptop against the wall. Instead be like, okay, I can't do B, I'll do part C. Let's see if I can do something there, try to get some points. Remember, probably 50% is enough for a 5. 55% is, I think, definitely enough for a 5, but I'm not sure. 50, 40, 30 is probably a good guess on this kind of test because it is very unusual conditions. So that's the goal we're looking at. So theoretically, this is not what you're going to do because you're going to rock both questions. But even if you totally bomb one of the questions, if you ace the other question, you have a very good chance of passing or even getting a high pass for the whole thing. So that's the math, just making sense of that. Okay. Remember that I've recommended type, copy, paste. If you go with pictures, that's fine too. That's your decision. If you do type, copy, paste, it might be a good idea to have the text format equation sheet, okay, available. So you have that ready to go. So you have that available. And, other things that I really should have for you, suggestions as to how to abbreviate constants, epsilon naught abbreviated as E0, and so on. Otherwise, I think those are words of wisdom. And remember to not push it to the last second. I say submit it before that clock hits 1 minute. I think you don't want to get into a situation where you are in panic mode in the last second trying to get that thing uploaded or submitted or whatever, because that could be tricky. So I hope those words are helpful. Other comments and or questions at this point as we're now approaching rapidly the end of the class?
Do they